Hello, chemistry students. We are going down the home stretch of talking about some various concepts, of various overarching concepts within chemistry, wrapping up the 2020 school year. We have talked about the different classifications of matter, and in our last video, we talked a little bit about how to separate out mixtures. And what techniques were used there. This video is going to talk a lot about solutions, and more specifically, when we had our last video, we talked about solutions and solubility and how solubility played a role in one of the separation techniques. We're going to talk about what a solution is and how solubility might be impacted by various factors. So that's what we're going to deal with in this video. It might be a little longer than the last couple. We'll see. Okay, so our learning objective for this one is describe how water acts as a solvent that dissolves solutes to form solutions in order to relate how the solvent properties of the water affect the Chesapeake Bay. The end of project that was associated with this unit was a Chesapeake Bay project, and actually under normal circumstances, COVID aside, we would do a project where the last project would be a big Chesapeake Bay project. That's not happening this year because of the pandemic issues, but we're going to go ahead and talk about, at least address the Chesapeake Bay. And for those of you who might be grabbing this video just randomly, we are based in what's called Sykesville, Maryland, the Century High School of Sykesville, Maryland. And the Chesapeake Bay is very, very important to the Marylanders, being that it is right dead center, and it's a major, major part of our ecosystem. So, first question that I would usually introduce is, what's the difference between a solution and a suspension? Well, if you remember from 2 videos ago, we did our classification of matter. They both appear very similar to one another, but the big difference is a solution is a homogeneous mixture and a suspension is a heterogeneous mixture. So you can see the particles in a suspension, but you cannot see the particles in a solution. We're going to talk about solutions here, the ones that are the homogeneous mixtures. So, water is the most abundant liquid on Earth and is necessary for all life. There's our classic Chesapeake Bay blue crab right there. One major property of water is it's a universal solvent. And you're going to, in biology next year, you are going to beat like a dead horse the concept of universal solvent of water. Water dissolves just about everything, especially those life critical components. Okay, there's Kool-Aid Man. Okay, water is fantastic, has fantastic at dissolving things, especially anything that has a charged component to it, because it will grab that apart. Water is polar. Water is like a mini magnet. So if it comes in contact with other things that are mini magnets, it goes ahead and pulls it apart and rips it apart and dissolves it very, very well. There's a water molecule. You got HOH. The O side of the molecule is kind of negative. The H side of the molecule is kind of positive. And hence you get this polarity, which we didn't get a chance to talk about too much, but this polarity where one side is negative, one side is plus, and actually water acts like a little mini magnet. Okay. Now we have a saying in chemistry of like dissolves like. Polar compounds will be dissolved in polar solutions, and non-polar compounds will be dissolved in non-polar solutions. So for instance, if a molecule has a plus or minus charge, or even has a plus or minus side, it's going to be able to be dissolved in water. So sodium chloride is dissolved in water because it's NaCl. Na is plus, Cl is minus. Sugar can dissolve in water, but wait, sugar is not ionic, does not have charges. Well, it has places on the molecule that has a slight positive side and a slight negative side, where there's a concentration of electrons making it negative. So we have a plus and a minus side to a sugar molecule. But gasoline, oil, all those petroleum products, there's nothing on there that has any charged particles to it, charged parts to it, so they do not dissolve in water. So here's an example of sugar which is dissolving. They talk about the solution, the water molecules grabbing the piece of the sugar and pulling it aside because the sugar has a spot on it that is attracted to the water. Okay. they talk about here is the fact it's really hard to find pure water. Now, in our classroom, you have the taps, not pure. You have our distilled water, our deionized water. Well, to the best of our abilities, that's as pure as we're going to be able to get it. It goes through a series of 4 different filters before we use it. So that is deionized water. We try to remove as much stuff as possible. It's not perfectly pure. There's still some stuff dissolved in there. Almost any sample of water you're going to have is going to contain something dissolved in it because, again, it is super, super, super soluble. And even better, when you get that pure water, as pure as you can get, and you leave it out on the desk, you know what it's going to grab? It's going to grab the carbon dioxide from the air. It's going to grab the oxygen from the air and dissolve that right into the water because water, oxygen, and carbon dioxide are both soluble in water. Hence the reason fish can breathe. As the stream is flowing down river, you've got that mixing and stirring, and what it's going to do is it's going to dissolve the dirt, dissolve the rocks, carry them, suspend them, and move them downstream. We talk about erosion when you did the rock and water cycle. And then finally, in really, really, really shallow waters, it's moving so aggressively, the water mixed with the air, the oxygen in the air, and hence helping to make sure that there's oxygen in the water for our wildlife to survive. So some other examples of solutions is like Coca-Cola or seltzer water or vinegar or food coloring water. Those are all solutions. They are homogeneous, means you can't see the particles. In Coca-Cola, you can't see any chunks. In seltzer water, you can't see any chunks. Vinegar, you can't see any chunks, but they are a mixture. It's a homogeneous mixture, so that makes it a solution. Solutions, we already said in a previous video, have 2 parts. They have the solvent and the solute. Solvent is the part that is doing the dissolving, and the solute is the part that's being dissolved. Normally the solvent is of a higher amount, and the solute is usually of a lower amount. The solvent can be any fluid, can be any substance, can be solid, liquid, or gas, but it's almost always liquid in our understanding of what a solution is, but it can also be a solid. Those alloys were actually solid solutions. And a solute is anything that can be dissolved in. So in the case of Coca-Cola, the gas bubbles, that's a solute. If you mix together different materials like alcohol and water into one container, that's a mixture of a liquid with another liquid. We've already talked about the solids like sugar or salt being dissolved into the solvent. So I take my sugar, mix it in water, and well, the sugar is the solute and the water is the solvent. Okay, so when you solute particles are evenly distributed throughout the solvent, we say that the solute has dissolved or is soluble, which simply means if I take my sugar and I mix them with my water, when I put them together, the materials will mix. However, if they don't mix or they don't mix thoroughly, then they are insoluble. And at a certain point, certain materials will just not be soluble because you added so much. So how does a solution form between water and other substances? Okay, so we've already said that water has plus and minus side, right? So the water has a plus and minus side. So if you look at this clip on the left-hand side, this thing in the middle with the blue and the purple, the green and the purple spots is an example of sodium chloride. Sodium chloride, the sodium is the purple balls, and the green ones, those are the chlorides. Sodiums are pluses, chlorides are minuses, and the things on the outside are the water molecules. Now, we already said the oxygen side of the water molecule is negative, and the hydrogen side of the water molecule is plus. So what's going to happen is the atoms that have charged slightly when the compound forms, the atoms have either a plus or minus charge. So those waters and those everything have a plus or minus charge. The water is attracted to the charged atom and they pull them out of structure. So the negative side of the water is attracted to the positive part of the sodium chloride. And the positive side of the water is attracted to the negative part of the sodium chloride. So you look here, and it's kind of weird to see, but you see like this one up here, where the purple one, we said the sodium, all the red spots are all attracted to it because the red side of the water is the negative side, and we said the purple sphere was the sodium. Sodium is plus, then red is the negative side, so they orient themselves that way. Over here on the right-hand side, we have an example of a green one. The green one is negative, so it is attracted to the positive side of water, and literally it just rips apart the material. They continue to pull until everything's surrounded by water, and you have a complete mixture. Now, whether something is soluble or not is dependent on two factors, two huge factors. Is the, I guess I would consider it one large factor. I just look at it, I guess I'll look at it as one large factor. Is the purple and the green more attracted to one another than they are to the water? If they're more attracted to one another, they stay together. Even though they may have charges, if they're more attracted to one another, they'll stay together. If they are more attracted to the water, they'll rip apart. So an example that I always throw out there is lead iodide, PbI2. Pb, a +2 charge. I, -1 charge. Definitely charged particles. But you put that in water, and those two particles are so attracted to one another that they don't break apart. And they stay together, and they do not dissolve. That's going to be insoluble because of the fact that it's more attracted to one another than they are to the water. Okay. What affects solubility? Well, there's a few factors. We already said like dissolves like, so polar dissolves nonpolar, polar dissolves nonpolar. So when a substance dissolves in another, if it dissolves in water, okay, it's polar, then it's going to dissolve something that has a charge. Polar, like dissolves like. And then nonpolar substances tend to dissolve nonpolar solvents. So if it doesn't have a charge, it tends to dissolve things that don't have solvent. So oil dissolves really, really well in gasoline. Both of those have no charges. Wax dissolves really, really well in gasoline. Both of those have no charges. That's where you're going to have a mixture. But wax will not dissolve in water, and oil will not dissolve in water because they are not alike. So there's a bunch of other factors besides just the chemistry that affect how quickly or how aggressively the dissolving takes place. First one is heating. So if you heat something up, obviously you're going to speed up the dissolving factor, and you're actually going to increase the amount that can be dissolved in most circumstances, especially if the solute is solid. You can stir it. I think we all know that if you just dump sugar into a cup, it doesn't dissolve very well. You have to kind of stir it. Or you can increase the surface area where you can grind up the component, you can grind up the mix so that it actually is more dissolvable. A sugar cube dissolves slower than granular sugar because a sugar cube only has the outside edges where water will come in contact with, whereas granular sugar, every single one of those grains can be attacked from all sides. So what's the difference between a dissolving and a reaction? They kind of seem very similar to one another, and actually the vocabulary is misused a lot. So if I were to take some nickel, which is what's on the left-hand side, that metal that's in this small tray, and dissolve it into hydrochloric acid, I would put it in, it'd mix, and suddenly, poof, it would go away. Well, that wouldn't be a dissolving, because what's happening here is the nickel is actually reacting with the hydrochloric acid. It's not dissolving. Just because it goes away does not mean that it is dissolving. In this case, it would be reacting. Dissolving is a physical change, meaning that if this were a dissolving process, I take nickel and hydrochloric acid, mix them together, and if I were to drive off the hydrochloric acid, what I would get back, if this was a dissolving, what I would get back would be the nickel, because nothing happened to the nickel. But in this situation, the nickel reacted with the chlorines and the hydrochloric acid to make nickel chloride. So this is not a dissolving process. This is not a solid dissolving process. This is a reaction. Dissolving is a physical change. You can reverse it with evaporation. Reaction is a chemical change. You cannot reverse it with evaporation. Now, we talk about the fact that this is all about the bay and our bay water. Our Chesapeake Bay water is a solution. Think about it. If you guys have ever been out to the bay and saw what's out there, it does not look like crystal clear water. As a matter of fact, our bay is probably more of a mixture than a lot of other areas ocean water. Okay, it's a solution. It's a solution. It's a mixture of a bunch of particles in there, all thoroughly mixed. Some suspended, but very, very thoroughly mixed in the material. So, what is the bay a mixture of? Well, I know of two things you should be absolutely sure of. It is a mixture of water and salt. Because the neat thing about our bay, our Chesapeake Bay, is the tributaries from above carry fresh rainwater and fresh water that is salt free, and the ocean on the base has very, 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 very high salt content. So when they mix in the middle, you have a gradient of different amounts of salt, and whenever you have a body of water that has a variable amount of salt in water, it's going to be referred to as brackish. It's going to be a mixture. So in really, really hot summer days, our Chesapeake Bay is very salty because not a lot of rain happens to the north. And when not a lot of rain happens, not a lot of fresh water is added to our bay, and the ocean water kind of trickles up and takes over a larger concentration. When we have our really, 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 really rainy seasons, that's when our bay happens to be much less salty. When I was a young chemist, I was involved in a study where we wanted to find out what the effect was, and I actually did this for one of my summers. Wanted to find out the effect of salt water on the Chesapeake Bay, where we were dealing with some rockfish. So we had this big setup where we had a bunch of rockfish, and we collected at a tributary of the bay, and we wanted to see throughout the season what happened to the growth and what happened to the mortality rate of our rockfish as the salt water changed. The unfortunate reality is Mother Nature doesn't play nice. It didn't rain the entire summer. It rained like deluge right before the project, so we had a really, really low really, really low salinity when we started. But as the season went on, it just became greater and greater. And honestly, those rockfish absolutely loved the salt water. So we realized that nothing was going to happen. They were going to grow pretty well. But we wanted to see this variability of the amount. And it literally, for 2 straight months of summer, it did not rain at all. So that's the end of this video. Hopefully you got something out of it. Everybody stay safe, stay healthy, practice that social distancing, and I will see you on the next video. Toodles.